Hello, and welcome to Lesson 13 of C.1, the Polar Ice Unit. I'm Meijin Chia, a high school teacher using OpenSciEd and an OpenSciEd facilitator. In this video, I will give an overview of Lesson 13 and wrap up with some tips and tricks. Lesson 13 is the final lesson in this unit and provides an opportunity for students to work with a computational model that includes many key ideas from the different lessons in this unit. First, let's briefly recap on how we got to Lesson 13. In Lesson 12, we calculate that about 3.35 times 10 to the power of 18 calories of energy transfers into the Illicit Glacier to cause the amount of ice melt that produces the yearly amount of meltwater from this glacier. And we calculate that about 5 times 10 to the power of 18 calories of annual energy flows into the Illicit Ice Fjord through convection. So we conclude that implementing the berm solution could significantly reduce the Illicit Glacier melt. In Lesson 13, we are wondering, how can we model what will happen to Earth's climate if humans make changes? Let's take a look at Lesson 13 at a high level. This is a putting the pieces together lesson that takes 3 45-minute days and 30 minutes of material preparation. There is no hands-on investigation, but students will need to use digital devices to manipulate the computational model. The video that introduces the computational model is highly informative and should be watched by teachers and students. There are 3 lesson chunks in this lesson. Let's see what's happening in each lesson chunk. In the first lesson chunk, students read about and discuss climate modeling. They figure out that a computational model could help us predict the effects of a changing climate. We wonder what questions we could test with the climate computational model. Later on in day 1, students are playing around with the computational model and start to narrow down to a specific question that they would test with this model. On day 2, they use the model to test their question and then discuss their findings. They conclude that it is possible for humans to implement solutions that can affect the climate with positive impacts, such as mitigating sea level rise and climate migration. Students are now ready to reflect on the unit and complete the end unit assessment. In the transfer task on day 3, students track the flow of energy and matter into, out of, and or within the heat pump system. They conclude that heat pumps provide a possible solution to help limit carbon dioxide emissions while keeping homes safe and comfortable. So in summary, in Lesson 13, students gain an understanding of how climate models are developed and what climate models are used for. Through testing the models, students conclude that a computational model shows that if humans implement solutions that decrease atmospheric carbon dioxide concentration or energy reaching Earth's surface, we can prevent some sea level rise and its negative impacts on people. Let's take a look at the key moments in Lesson 13. The reading in Part 2 of this lesson highlights a couple of ideas, such as the difference between weather and climate, the differing purpose of weather versus climate models, and how computational models are developed. An extension opportunity mentioned in the teacher edition is going back to computational models that students used earlier in the unit, such as the sea level rise simulation, to consider the equations, assumptions, and limitations of these models. Developing and testing a question with a computational model was a productive challenge for students. They had to consider how an implementable human solution could affect one of the independent variables in a computational model. I could also assess students' proficiency at tracking and explaining the changes in energy and matter flow shown in the model. The teacher edition notes that this activity is intended to build hope by encouraging students to focus on how various human solutions could affect the climate positively if carried out. In the heat pumps transfer task, students demonstrate proficiency in 2 science practices. Firstly, using models, as students interpret the heat pump system models as well as particle level models of the refrigerant at different points in the heat pump system. And number two, planning and investigation. Students play a role as HVAC technicians tasked to repair the heat pump HVAC system. Students have to construct a directional hypothesis, determine the variables, and how to collect data to troubleshoot the system. At the end of Unit 1, students have ideas about matter and energy. For example, they know that matter is composed of atoms and molecules. In Unit 2, students expand their understanding of matter. For example, they figure out that atoms have positive nuclei and mobile negative electrons. They also learn that energy can be transferred into, stored, and transferred out of electric fields. Additionally, Unit 2 brings in key ideas related to forces, such as electric forces are attractive between unlike charges and repulsive between like charges. Okay, let me share a couple of strategies for this lesson. As I mentioned previously, the introduction to the computational model video shows how to test the model by changing one or more of the model's independent variable. To test their questions, students could learn how to add one or more factors into their model as independent variables. I have provided a tiny URL link to the Sage Modeler tutorial if you're interested in teaching students how to do this. For a more straightforward but less accurate way to modify the computational model, students can also double-click on a factor. A box will then pop up, as I show here on the slide, and enable them to change how and how much one factor affects another factor via the drop-down selections, as shown in the bubble. For example, we could justify that cloud seeding would change the effects of an increase in volcanic ash in the atmosphere to decrease light reaching Earth's surface from the default of a little to a lot. For the heat pump transfer task, I found that students struggled to understand the boundaries of the heat pump system. So I modified the schematic of winter heating with a heat pump system to assist students in considering the energy inputs and outputs of the heat pump system. For a helpful resource, the link provided goes to a practical guide on how to make transfer tasks work. This guide is one of many articles in the OpenSciEd on-demand support library that may be useful for you. Students encounter climate model through the reading in part 2 of this lesson. At the start of this lesson, we referenced the unit Gotta Have It checklist from the previous class session. To reflect on the unit, students look back at the driving questions handout from Lesson 7 and the driving question board from Lesson 1. Thank you so much for watching. Stay tuned for more videos about other units in the high school chemistry course.